Now, I'm pleased to bring to the conversation Gal and Liron from NVIDIA. Liron and Gal have a very interesting session. Liron, she's the director of developer relationship within NVIDIA, and Gal is a data scientist. Um, so go ahead, I'll hand it over to you. Present yourself, and good luck. Thank you very much. I think you muted. Liron?
Yeah, sorry. My bad. And now you can hear me?
Yes.
Yes.
Okay, very good. So first of all, thank you for joining. This is my first webinar, so wish me good luck. And what we're going to talk about is something called NGC, short for NVIDIA GPU Cloud. It's not a cloud, it's actually a marketplace with a lot of software that NVIDIA is giving to the community for free for anyone using our GPUs. I've been in NVIDIA for 2 years. I'm the director of the developer relations, which basically means that I work with, talk with, teach, educate, help developers everywhere, startups, big companies, researchers at the university that use our GPUs or want to use our GPUs, and basically help them accelerate their work. A minute about NVIDIA. I assume most of you know NVIDIA, but a little bit of history. So NVIDIA is the maker of GPUs, graphic processing units. GPUs started their life in gaming. So for all of you who are gamers, probably know NVIDIA because we're very good in gaming. This was back in the 90s. After a few years of gaming, we naturally evolved into graphics and graphic design. So everybody doing anything that has to do with graphic design uses our GPUs. And about 8 years ago, something very interesting happened. The whole idea of neural networks and deep learning was something that was basically only in academia, and it was taking a very, very long time for these algorithms to work. They were running on many CPUs, and actually someone at the university took a GPU and started running neural networks and doing deep learning on GPUs, and actually found that it was working much faster. The accuracy of these algorithms went up, the training times of these algorithms went up, and he wrote a paper about it. And the paper came to NVIDIA, and the story is that Jensen, our CEO, actually took half of the company and said, guys, this is what I want you guys to work on. You were working on AI and getting AI on our GPUs. And that was around 8 years ago. We call it the big bang of deep learning. And basically, ever since then, we've been working both on our hardware, on our GPUs, and on a very large software stack that not everybody knows that is available. And the software stack is there for the data scientists to help accelerate their work. Azure today has most of our GPUs available. Actually, we just had a big announcement a couple of weeks back, where our newest GPU that is dedicated for inferencing is also now available on Azure. So you have a full stack of training GPUs and inferencing GPUs. And basically, how NVIDIA is working today is we're split into verticals. So as you can see from the first slide, NVIDIA today concentrates on a number of verticals where we see AI helping the most. So we have autonomous driving, fraud detection, medical imaging, and healthcare in general, telecom. All these are verticals within NVIDIA where we develop software in order to help accelerate any development being done there. What are the challenges of working in AI? Well, first of all, in order to make an environment, an optimized environment, you have to install many different flavors of different software. You have to optimize it to the GPUs. And of course, you want to optimize your productivity. So NVIDIA's answer to that is something that we call NGC, NVIDIA GPU Cloud. And basically, it's a set of tools, which you'll see here, that help you accelerate your work. So let's start with the basics. First of all, NVIDIA is a big believer in containers. We work only Linux-based containers, and that's what you'll find in NGC. You'll find over 50 containers of different software. Together, you'll find pre-trained models that NVIDIA trains and optimizes on the GPUs. You'll find model scripts. These scripts help you train your algorithms yourselves. So you can take a pre-trained model from NVIDIA and just do some type of transfer learning with our model scripts. And that'll really help you accelerate your work because you don't have to train models from scratch. And lastly, on top of our containers and our models, we also have industry solutions. We have SDKs specific for industries. I won't get into it today, neither will Gal, but I do recommend that you guys look into NGC. And if you're working in a specific vertical, we have a video analytics tool to help to handle the pipelines of different streams. We have medical imaging tool that's an annotation and running models. We have different industry solutions for smart cities. So we really tried to develop and accelerate work, A, by containers, and B, by SDKs for specific verticals. So what's special about our containers? First of all, they're optimized for our GPUs. When you run an NVIDIA container, it actually recognizes the GPU it's running on and knows to get the most out of it and to optimize the work. It's scalable once you get into multi-GPU. Today, we see a lot of deep learning going from one GPU-based training to multi-GPU training. It's designed for enterprises, not for small-scale training with a little bit of data, but for really large-scale training and a lot of data. And what do we have? So first of all, any deep learning framework is available. TensorFlow, PyTorch, Caffe, MXNet, whatever deep learning software that you're using is already optimized on NVIDIA. We work with a lot of startups and companies, by the way, that once they moved to NVIDIA container, TensorFlow container, PyTorch container, they received a ramp up of training times just from this container. For classic machine learning, we have something called Rapids, which basically takes Pandas, sklearn, XGBoost, very classical machine learning algorithms, and boosts them to run over our GPUs. We have what's called HPC, or high processing containers. It's more for third parties and applications that today run on GPUs and accelerate. So we have a lot of like genomics software. And we also have tools for inferencing, where you see TensorRT is tools for inferencing. Another thing that we do is something called mixed precision. We believe that once you train your algorithm, you can also train it in mixed precision, which is basically training it in half FP16, half FP32. And we actually have something called AMP that Gal is going to talk about. It's an automatic mixed precision automation, which will help you run training in mixed precision, which will cut training times and also boost inference times. So as you can see from this graph, we have continual performance improvements within our containers. You can see just from a few months differences, the performance raises all the time. And this is the software that NVIDIA keeps on developing over our GPUs in order to help accelerate everybody's work. Like I said, we have pre-trained models. You can see here, this is what NGC looks like. You have ResNet, GoogleNet, VGGs. You also have a lot of medical pre-trained models. So we have, I think, around 13, if not more, body parts that we've trained over CT, MRI that you can take, heart, liver, lung. And all these models are open source. You can take them and you can just do transfer learning with your own data. which basically helps you cut down a lot of times. Again, they're optimized. They run the best on GPUs. They know to understand which GPU you're running on and give it the best optimization. And of course, we have our model scripts, like I said, which help you manage your training times the best. Like I said, I won't go into industry solutions because of the time we have. I'll hand it over to Gal. What I suggest, again, if you write down in Google NVIDIA NGC, create a user, go in, see what's over there. There's a lot of goodies for people using our GPUs. Gal, over to you.
Okay, thank you, Liron. Hello, everybody. My name is Gal. I'm a data scientist from NVIDIA. And today I want to cover a few topics that could help you improve your deep learning training, inferencing, and the environment building. So I'll start with sharing my screen. I don't have slides, but I'll share some links. Okay. All right. So as everyone said, I will start from NGC. NGC, it's NVIDIA GPU Cloud. It's not a cloud. It's a container registry for Docker containers. We have here a lot of containers, more than 50 containers of the popular frameworks such as the TensorFlow, PyTorch, MXNet, TensorRT that I'm going to cover this topic also. Rapids, a tool for machine learning, also models, pre-trained models, and model scripts. And when I say model scripts, it's a great documentation for example, for BERT, how to train BERT, to download data, to fine tune, and all the things you need to know about it. And yeah, this is a really good stuff. And by the way, about containers, so let's see, for example, TensorFlow. So here on the first line, we have the Docker pull command. So you can download the TensorFlow. There is examples on how to run this container. Some Docker commands like if you want to use to do an interactive session, to use a file system with our Docker container, or also if you want to use another release. So you can find the release note, and for example, 1907, let's see. Here we can see we have TensorFlow 114. So you can go here and find your specific framework. Okay. Now let's talk about training a bit. I want to start with MultiGPU Training, and I want to talk on Orvod. Orvod, it's an open source tool from Uber that's built based on OpenMPI, on MPI multiprocess interface, and try to make a distributed training easy to use and fast. And I want to go through an example, a TensorFlow example. Yeah, so here's the example. So here it's a part of some toy example of TensorFlow, and we can see only the parts of Orvod. So let's start. The first thing is to import Orvod. In this case, on TensorFlow, we need the Orvod from Orvod to take TensorFlow library. So we started with init, the Orvod. Then we need to make a config, and to tell this config how much GPU do we have. So Orvod.local rank is the number of GPUs. Then you build your own loss function, and we need to build an optimizer. So there is a Here in this example, you can see that the learning rate, we multiply the learning rate by the overbot size. So there is a rule that says that when we're increasing the batch size, and in this particular example, we're doing a data parallel. So data parallels, it said that we take the model, duplicate it across few GPUs, and then increase our batch size and send different batch size to each GPU. So here in this example, we multiply the learning rate by the batch size, and this is the recommendation, to multiply the batch size, to multiply the learning rate with the Harvard size, with the number of GPUs. Second thing is to use a distributed optimizer, because we're going to use a few models, and in multi-GPU training, specifically in data parallel, we want to average the gradients. So we train for each GPU the model, but then in the end of the batch, we want to average the gradient. So there is an algorithm called the all reduce that does it between the GPUs and don't need the CPU communication. The GPUs can talk between themselves. So this is why we need a distributed optimizer. Second, we need to build hooks that will broadcast the variables. So we have the first rank 0, but we need to broadcast all the parameters for all the GPUs. So this is this hook. Then, train off. We try to minimize the loss, and then here we save the checkpoint only if rank is equal to 0. So it said that only with the first GPU we will save the checkpoint. All right, and then we're running a session. Here it's a monitor training session, and we're using the hooks. And then every single iteration, it will broadcast the parameters. So how to run it? For run it, because we're using Harvard and Harvard-based MPI, we need to run a Harvard run minus NP, number processes. So here we have 4 GPUs, for example, so we are using 4 processes. And our host is a localhost. We're running on the localhost network, and we have 4 GPU, and the script, the command, it's Python train.py. Right. By the way, I will share all these links in the end of the session in the comments below. So let's go ahead. Let's continue. I want to go through automatic mix precision. Liron talked about it, about automatic mix precision. Before I starting with it, I want to say a few things about the new GPUs. So in the new GPUs, let's say V100, there is an hardware accelerators called tensor cores. These tensor cores can multiply 4x4 matrix with 4x4 matrix in 1 clock instead of 12 or 13 clocks. So, and that can be only with mixed precision weights, or let's say FP16, or mixed precision, it says FP16 multiply FP16 plus FP32, that this plus, it's the bias head. So if you have tensor cores, I'm recommending to use this tool, the automatic mixed precision, and this tool is very straightforward. You just need, let's go to TensorFlow examples. So this is what I said, 4x4 multiplying 4x4 plus the biases, and all these happen in 1 clock. So in TensorFlow, from TF 1903, you can export this variable in the Linux environment, or just in your code to run OSN run and run this parameter, this env command inside your code. And when you do it, you done. The model will train with mixed precision weights. And when I said mixed precision, it said that our base weights they are in FP32, but only the calculations run on FP16. All right. There is an examples of PyTorch and on MXNet. So again, I'll share these links. So let's go to TensorRT. Okay, so TensorRT, it's a tool for inferencing to optimize inference task. And I want to go over the things that TensorRT does. So as input, we got the trained neural network, our weight file, PB file, for example, from TensorFlow. So in this particular case, you need to move it to another format, but the trained neural network, and the output is an optimized inference engine. And when I say optimized inference engine, it's TensorRT engine, TRT engine. And what it does, it's first of all, precision calibration. When I say precision calibration, I mean that it's if your neural network trained with FP32 weights, with precision calibration, we can change the weights to FP16 or int8. And if we have tensor cores, we can improve our performance by, I can say, 10x. So this is the precision calibration, to change the precision of the weights. Second thing, layered tensor fusion. So in neural networks, a lot of layers are going like conv, and then activation, and then biased. And it's repeating itself a lot of time in the network. And on GPU, to change kernels, it's very expensive because we have a lot of cores and a lot of registers. So this layer in tensor fusion takes these layers and combine them, fusion them into one layer. And that reduces the kernel switching on the GPU. First thing, it's the kernel auto-tuning. So kernel auto-tuning, when we use this engine, when we optimize the neural network with TensorRT, when we're building the engine, this TensorRT detect the GPU that we're using at this moment and optimize the network to this GPU. Multi-stream execution. So in CUDA, basically, we can use one stream or few streams. And this TensorRT can implement a multi-stream execution that instead of waiting batch by batch in the inference time, it could stream it by multiple streams. And that improved the performance. And last thing, dynamic tensor memory. It said that the batch size could be dynamic. So it could be 8, it could be 64. It's dynamic batch size. All right, that's it on TensorRT. There is a lot of samples here, code samples, how to use TensorRT. There is a TRT exec. This is what build the engine. It's a command line that build the engine. And if you want to start and play with this, go to NGC, NVIDIA GPU Cloud, and you can find TensorRT container, download the container, run it, and all the samples are inside the container. You can try it. That's it from my side. Thank you, guys. Thank you for listening to me. That's it. Thank you.
Thank you, Gal, and thank you, Liron. Thank you for being with us in the Hackorona webinar. And it was very interesting. So thank you very much. I'm going to remove you from the stream now. So again, thank you very much. It was a pleasure to have you with us.
Thank you.
So this is it. We just finished our daily webinar. We will be here tomorrow as well, the same time. 2 interesting sessions. So join us tomorrow. We're waiting for you. And have a good evening. Bye-bye.